And now the final indeterminate form that we're going to look at is all the ones that involve the exponents. And there's just, again, kind of one trick you have to do at the start, and then you end up using L'Hopital's rule. All right, so evaluate the following limit. The limit is x goes to infinity of x raised to the 1 over x. So when I try to plug in infinity, I'm getting infinity on the bottom. Raised to the 1 over infinity is 0. So which one's going to win out? Infinity raised to anything should be a really big number, but anything raised to the 0 should just be 1. All right, so which one's going to win out? All right, and the problem here is we're dealing with an exponent, not a super nice exponent either. All right, it's 1 over x. All right, and here's why we reviewed logarithms before doing this section. All right, because we're going to actually end up using logarithms here. So let's just call this y. And logarithms give me a nice thing where I can use logarithms in order to take out exponents. So what I'm going to do is take the natural log of both sides of this equation. What seems like I'm just making the problem harder. I'm introducing a natural log where there wasn't one. But now on the right-hand side, because I have this exponent, I can rewrite this as that. And now what happens if I try to plug infinity into this? All right, this is natural log of x over x. If I try to plug infinity to natural log, I get infinity. If I try to plug natural log into x, I get infinity. All right, so now I can use L'Hopital's rule. And L'Hopital's rule says, take the derivative of the top, it's going to be 1 over x. I don't know why I'm writing like this now. Oh, using the wrong thing. All right, 1 over x over 1, which is just 1 over x. And when I plug in infinity into 1 over x, I get 0. All right, so if I evaluate this limit, I get 0. All right, so one common thing is people just saying this is the final answer. But that's not going to be the case. Right? The final answer is not going to be that 0. And why is that? Because this answer, all right, goes back to here, which is the natural log of y. So the natural log of our answer is equal to 0. How do we get back to our actual answer? We raise both sides to the e, which cancels out on the left. On the right, we get e to the 0, which is 1. So my actual answer is going to be 1. So really, this is going to be the case in a few different things. If you have this exponent that's more difficult than just a single variable or number, you can take the natural log of both sides of your equation, and that gets rid of the exponent. You end up having to deal with natural logs, but at least you can do that. But you have to remember at the end to go back and kind of undo that natural log process by taking both sides and raising them to the e. All right, one more example, and again, you can see it's the same, x raised to the sine of x. All right, on the bottom, we'd have 0. On the top, sine of x is 0, so 0 raised to the 0. Again, 0 raised to anything should probably be 0. Anything raised to the 0 should be 1, so these are kind of two things that are competing. But we'll do the same thing. We'll call y x raised to the sine of x. We'll take the natural log of both sides. And that allows us to bring the sine of x out in front. All right, so now what happens if I want to try to plug in 0 into this? All right, sine of 0 is 0. Natural log of 0 is infinity. So this is one of our indeterminate forms from earlier in this video set. And the way we dealt with that is we're going to rewrite this as moving one of the things to the bottom as a 1 over thing. All right, so if I want to evaluate this, we could go two different routes. So in the ones we did earlier, it's always going to be easier just to move an x to the bottom. But here we have two different functions. We have sine and natural log. So our two options would be to write this as sine of x over 1 over the natural log of x. All right, so that's option 1. Option 2 would be to write this as the natural log of x over 1 over sine of x. Just using the same process we did of moving something to the bottom and writing it as the fraction. That way it's the same expression, but now we have either 0 over 0 on the top option or infinity over infinity on the bottom option. If we try to do the top option, the top derivative is pretty simple. But the bottom option, you'd write this as natural log of x to the -1. It'd be negative natural log of x to the -2. times the derivative of the inside, which is 1 over x. All right, so that's option 1 if we do L'Hopital's rule. Option 2, if we do L'Hopital's rule, derivative of the top is 1 over x. Well, the bottom, 1 over sine is just a trig function. All right, that is cosecant of x. And we learned the derivative of cosecant of x before. That's negative cosecant of x, cotangent of x. So which one of these looks simpler? All right, the one that looks simpler is the one that doesn't have any more natural logs in it. All right, so this option is going to be the one we end up wanting to do. And at the start, there's never really a way you're going to know which option to do in these 0 times infinity cases, unless one of them is just an x. That's always the easiest to move to the bottom. But when you have kind of 2 different functions, you might have to try one, see if it makes your equation really complicated, or see if it actually kind of keeps it at the same level. All right, but then if we try to evaluate this, we'll get a bunch of zeros all over the place. So one thing that's going to be helpful here actually will seem like it's going to make the problem more complicated at the start. All right, cosecant is, I can write this x down on the bottom now because it's 1 over. All right, cosecant is 1 over sine. Cotangent is cosine over sine. And whenever you have the bottom of a fraction already in the bottom, so these 2 denominators, all right, I can multiply the top and bottom by sine of x. It's going to end up looking like this. Which seems counterintuitive, but this allows me to actually plug in 0. So if I try to plug in 0 here, I just get a bunch of undefined things. You can't plug in 0 into cosecant or cotangent, but by transferring it back to the original sine and cosine, I can. And now I plug in 0, and I get 0 over 0. Which, again, doesn't help me too much. What I'm going to do now, instead of doing that, and this is a lot of stuff in one problem, is rewrite this as and then when I plug in 0, all right, this is a problem that's come up a lot, sine of x over x. All right, when you take that limit, you get 1. I have an extra negative sign, so it's going to give me -1. Sine of x over cosine of x, if I plug in 0, I get 0. So my final answer is -1 times 0 is 0. Which is going to be my final answer for the whole problem is going to be 1. Because this is the natural log of my answer equals 0. Raise both sides to the e, you get 1. All right, so there's a lot going on in that problem. I think this step here doesn't really make that much sense. It might not be obvious to do that. You might end up doing L'Hopital's rule again and making it more complicated. But there's these small little tricks of kind of using sine and cosine to your advantage. And this is one of them, of rewriting things in terms of sine and cosine. So you have things moving to the top of the fraction and you don't get as many undefined terms. All right, so the last one might have been confusing, but the process is still going to work. So try this problem on your own. All right, see if you can understand how to do these indeterminate forms with an exponent. All right, it's going to be similar to the previous ones, hopefully with less trig.